Hi there and welcome to the screencast for Lab 3. So I'm going to start by changing the author field there. Okay, so in this lab we're looking at a data set on petrels, so white-chinned petrels, which of course are a bird that were caught by fishing vessels essentially between 2000 and 2003 off the coast of New Zealand, or in some cases quite far off the coast. We have a large number of variables here in this data set that you could explore if you wish, but the primary ones we're going to look at are the area in which they were caught. So that's going to have essentially this is location, so there's 6 different locations, and then we're going to look at the right wing length as a proxy for size, and then we're going to see if there's any differences by sex. So we're going to start off by loading our ggplot library in and loading the data in and taking a quick look at the summary. So you can see there's a number of variables. We've got autopsy, year, month, longitude, and so on. We've got some label variables, sex and area. Okay, so they're the label variables there, and then we've got the right wing length there. And you can see that in many of them there's a bunch of missing values. So there's NAs, which is short for not available. Okay, so to make our job a little bit easier for later on, we're just going to get rid of any row that has an NA. So at the moment you'll see that our data has 722 observations, right? But we're going to get rid of a number of the NAs using the NA-omit function. So I'll run that code there. And then you can see that when we do the summary we have no NAs left, and we are down to 659 observations. So we're going to be using the Petrels data set rather than the all Petrels data set here. So we're going to start by seeing if there's any difference between sex. So is there any difference in the size of birds? Proxy for size is going to be the right wing length by sex. And then is there any difference by area? And then we might look to see if there's some potential confounding between these two variables. Okay, so we're going to start off by just assessing how many birds of each sex are in each area. So we can do that with the table function. Okay, and when we do that we notice that there's varying numbers in terms of the total. So in area C there's only 13 birds, in area F there's only 12 birds, whereas in area A there's 250. And we can also see that the proportion changes, doesn't it, between areas. So in area F it's 50-50, whereas in area E there's a much lower proportion of females, probably about 13-14%, right? Whereas it's more like 20% in area A. So the proportion of male and female birds in each area differs a bit. E.g. area E seems to have a higher proportion of males. So we can do this with a bar chart instead, of course. So instead of a table we could use a bar chart. So we could use our ggplot. Remember our recipe, we put our data into the ggplot argument. We then put our mapping from our data to features of the plot inside our geometry, and we're using a bar chart, so we're using geombar. So let's run that. And you can see that by default here it stacks the bars. I might make this just a little bit smaller so that we can see the code and the graph in the same plot, in the same sort of screen. So you can see that by default, because I've filled by sex, it has stacked the bars, and that's fine. It allows us to see the total number easily in each of the areas, so you can see that it differs quite widely, but it's harder to tell whether there's a difference in proportion, though perhaps we might get a hint, and it certainly seems in area E there's a higher proportion of males compared to females than the other areas. It's a little bit hard to see the number to compare the number of females across groups. It's not too bad in this case because they're quite different, but if they were similar it would be hard to compare these, and that's because they're starting at a different baseline. So let's copy and paste that, and we'll add position equals dodge. You remember that when we add things to the geometry that aren't from our data. So here we're just altering the position of the bars, or the method that's used to position the bars. And the dodged bit isn't from our data. It's not like sex and area, which come from our data. So it doesn't go inside the AES bit. Instead, it just goes inside the geom bit. So we have the mapping argument here, then a comma, then the position argument. Okay, so arguments within a function are separated by commas and are labelled. The order doesn't matter. I could put it in the other order if I wanted to. So here's a dodged graph where everything is now at the baseline. And with this one, it's easy to assess that there's differences in the number of males and differences in the number of females. But again, it's hard to assess proportions here, which is perhaps the thing that we're particularly interested in. We could try another position argument for that. Position equals fill. And when I run that, what it does is it takes this one and essentially it stretches all the bars up so they're all the same length. So that, and of length 1 essentially, so it normalizes the scale so that we directly have proportions. So if you like, it's converting the data to proportions and then plotting the proportions in a stacked bar chart. And so we can easily compare the proportion of female and male across the different groups here. And we can easily see that E has the largest proportion of male. Okay, so let's write a little bit about that. Stack, which is the default, allows us to easily compare one group, males in this case, which are at the baseline, and the total across groups, but hard to compare, or harder to compare the total count of females across areas as they start at a different baseline. Also a little tricky to compare proportions. Position equals position equals dodge allows us to easily compare counts in every group sex across areas, but hard to compare proportions. Position equals fill makes it easy to compare proportions. Across areas, but we lose count information. So which one makes sense just depends on the question you're answering. In this case, we're particularly interested in, is the proportion of male and female different across the groups, and so this graph here is probably the best one. Okay, right. So let's investigate the distribution of right wing lengths between the sexes. I'm just going to maybe close that document down and reopen it, just because it's doing something odd with the window there. So you remember that we could look back to Lab 2 for how to do this. So we want the distribution of right wing lengths, and we could use a variety of different things. So let's jump back to Lab 2, where we looked at the distribution of heart girth, or height by body weight. Body weight by sex. That would be a perfect one to copy, because essentially we want to do the same thing here, except we want to use right wing length instead of body weight, right? So we've got a histogram here. Let's start with the histogram maybe. We'll grab that and we'll just copy and paste that there. Okay, so in general you should be doing this all the time, copying and pasting stuff, and then just fixing it up so that it works, right? So we're going to be using our Petrels data here, and then the columns and then the distribution we're interested in is the right wing length. So what I'm going to do to figure that out is I'm just going to go back out to the top here, and where I've done my summary, I can see the name of that column that I want, so I can copy that and paste it down. And the reason I'm copying and pasting rather than just typing things in is it's much harder to get it wrong. There we go there. Right, so there's a histogram of the right wing length. Now we want this per sex, so maybe we want to colour the bars in by the sex. So we might try something like this. Now, just like the bar plot does, by default this stacks, okay, which means that we can easily see the distribution of the males and we can see the distribution of the total, but it's hard to see the distribution of the females here because they're starting at the different baseline, right? So again, we could use things like position equals dodge, just in the same way. Essentially what's happening with the histogram is that the histogram's doing some computation to figure out how many observations are in each bar, basically, in each bin that we're supplying, and then it's calling the bar plot function to draw it. Okay, so by dodging it, we can see the distribution of the males and the distribution of females. And I think here that it looks to me as though the distribution of the males are just maybe shifted a little bit to the right. Right, the centre of the females is down here at about the sort of low to mid 380s, whereas the distribution of the males is maybe centred a little bit closer to 390. Okay, we could also try these other ones, so the density or the box plot. So let's grab that whole code chunk, copy and paste, and we will change it to a density. Now, of course, with the density, we don't need the bins or the position equals dodge, but instead we're going to want to add some transparency here. Okay, so make them a bit see-through. Oh, that's probably a little bit too see-through. There we go, something like that. Okay, so again, my conclusion is kind of similar, right? The actual shape of these distributions are quite similar, but there's maybe a small shift in centre where the blue one has moved a little bit up to the right. It's not perfectly symmetric. It's not too bad. There's a few more sort of extreme small right wing lengths than there are extreme large, but generally it's not too bad. We might want to do box plots as well. So when we do a box plot, what we're going to want is we're going to, so we could do the exact same command. Let's just try that out. We don't need the alpha. When we do, we notice that we get right wing length here, and we can easily compare the groups because we've got sex there, but notice that we've got some odd scale here. Right, and this scale is actually completely arbitrary, and all it is because there's actually nothing specifying what Y should be. So in here we've got a guide over here telling us what the colours are, but in fact we could actually just put male and female there, couldn't we? So instead of fill equals sex, we could actually just put Y equals sex. Okay, and of course we could still colour them in if we want to. Right, so maybe we could use the colour. But then of course the guide isn't useful because we already know that, so maybe we could turn the guide off. So it's the colour guide is going to be none. There we go. That's how you turn a guide off. I think null might also work. Let's try that. No, that doesn't work. None works. Okay, so again we see that the shapes are pretty similar between the two, but the whole of the box plot for the males has been shifted up a little bit compared to the females. There's not a massive difference, right, compared to the range in the data that we have. There's not a huge shift, but there does seem to be a shift in the centre and a shift in the average. Okay, so males seem to be a little bit larger on average compared to females, maybe about 3 to 5 units or so. Units, millimeters. I guess we could just say maybe about 3 or 5 millimeters or so. The distributions are otherwise pretty similar. There's quite a bit of overlap in individual in the distributions. Okay, so while we're not saying that all males are bigger than females, clearly they're not because they overlap a lot, we are saying that on average they're shifted up a little bit. And it's only a little bit, right? So whether this is statistically important is what we're going to assess later on, because this, of course, this is just a sample, right? If we took a different sample, then maybe we'd get, maybe the direction of the effect here might be different, and the females that we get in our different sample might be slightly bigger on average than the males, right? So this is where the power of inference comes in later on. So is kind of saying, essentially, we're comparing it to some random case. So we're comparing what we see in our graph to what we'd expect due to random variation. So we'll see that later on. Okay, so that's sex. So our conclusion is males are bigger than females. Right. So we'll do the same thing for area. We've got some code here. Again, we could use box plots, histograms, or densities. We're going to do a bunch of different plots and see what we can find. So here's some histograms. So instead of colouring it like we did up here and dodging it, because there's 6 groups, that's not going to look very good, right? And so instead, I have used this facet wrap command here, which essentially just splits the data up by area and does a histogram per one, plotting everything on the same scale so that they're comparable. Okay. Now there's probably too many bins. Let's reduce the number of bins a bit. There we go. Okay. So I think you can see here that that this isn't fantastic to compare the groups. We can compare A and D easily because they are on the same scale above each other, and similarly we can compare B or E. Clearly E has a higher distribution than B does. C and F, of course, have very little data, but it's hard to compare, say, A and E here because we have to sort of refer back to the scale all the time. So you can see that A is centered maybe at about 390, E is centered maybe a little bit higher. So you can sort of infer that maybe E is the group that's shifted to the right the most. We can't say much about C and F because there's not many data points there. And maybe D is the one that's the smallest. Hard to tell, right? There's probably lots of overlap between A, B, and D. So that's histograms. We could try densities. So let's try some densities. So we could try, let's try fill equals area. So we'll just essentially do the same as what we did before. Okay, that's a bit messy, right? So there are too many groups. So the trick that we used here for putting 2 groups on top of each other and having them a bit see-through to compare has its limits. Right, it only works for maybe 2-3 groups. It sort of depends on how separate they are, because a lot of these groups are actually in a similar location. It's kind of hard to see. Nonetheless, our conclusion here is probably that E is bigger, right? So this is E here, that colour there. So we're getting some information from the graph, but it's perhaps not ideal. We could, of course, again facet wrap this. So we could facet wrap by area. And we could even force them to be all on top of each other by specifying the number of columns to be 1. Then they're all on top of each other and we can compare directly. I don't think this is necessarily ideal because there's quite a lot of additional space taken up by the labels, which we don't really need. You could get rid of all that, but it's a bit fiddly to get rid of all that because we've got the labels down here, of course. So there are other geometries that can be used to essentially get this same thing, but without the A, B, C, and D, E, and F labels taking up space. And essentially what you do is you remove the A down here because of these numbers on the densities here aren't that useful. So you can use, I think it's called geom ridge lines for that. If you want to Google, so geom ridge lines. Okay, right, and we might look at box plots as well. And box plots are really the one that's going to work well for this data. Basically, box plots work well whenever you have more than a couple of groups. They tend to be the best. So let's get rid of the faceting. Switch to a box plot, and just like we did before, we're going to put area on the y-axis, so we can get rid of the alpha. And there they are there. Right, so again here you can see that the E group is higher than the others. Now the disadvantage with the box plot is we lose sample size information. So we don't know, for example, that F here only has 12 observations in it, and so does C, or C has 13 I think, but we sort of lose that information a little bit. But nonetheless we can see that the E group is probably the highest. These ones are all similar, and then A is in between. Okay, so area E birds, so the box plot is probably the most concise summary of these data. They work nicely whenever we are comparing multiple groups, comparing a numeric measure across multiple groups. The area E groups have larger right wing length compared to the other to birds in other areas, have larger right wing length on average compared to birds in other areas. Okay, so considering what we found so far, what might explain the larger birds in area E? So we need to kind of look back and see what we found. So we found that area E birds are bigger. We also found that males were bigger. And we also found that area E had a higher proportion of males. So it might be that when we look at all area E birds, we're just measuring more males, and because we're measuring more males and males are bigger, it looks as though area E birds are bigger, but it's just due to the fact that there's more males. Right? So this is getting you into the mindset of thinking about what might be going on here. Is the effect that I see between the two variables, right wing length and area, is that actually being influenced by some other variable that I have? So is there some confounding there? Okay, so area E birds are bigger, but so are males. And area E has more males, has a higher proportion of males. So maybe the larger birds in area E are just because we have more males there. Right, so we could easily look at that, right? Because we could just say, well, you know, potentially the effect that we see here in area E is just because we've got more male birds, so why not just do the same plot for males only, and then we take out the sex effect, right? Because there's only males being looked at, so if the area E males are bigger than all of the other males, then that suggests that area E birds are bigger, at least in the males. We could do the same thing for females as well, right? So we're just going to redo these same plots, but split up by area and sex. And I think the best one to do is probably the box plot, because that's the most concise. But we might try some others as well. So what we're going to do is rerun that, and now we want to split this up by sex. So we're just going to add some colour for sex. There we go there. And because there's so many of them, and due to the aspect ratio of the plot, right, so because there's like 12 box plots here, they all have to squish into the height. The width is bigger, so swapping the role of X and Y will probably give me a nicer looking plot. So let's do that. I just swap Y and X around. There we go. Okay. So what I see here is that within the red ones, the E group is a little bit bigger. Not hugely so. The A group's not too far behind, but bigger compared to the other ones at least. And within the blue groups, again, area E is bigger. Okay, so the effect of area E being bigger is not due to sex, because within the males they're bigger and within the females they're bigger, so regardless of sex, they're bigger. Okay, so it's not due to the differential proportions. This plot is also quite good because it allows you to compare the male and females within each area. So you can see that generally within each area, excluding maybe F, where we don't have much data of course, and maybe A, it's a little bit unclear. The box is at least a little bit higher, but the median isn't. So there's a little bit equivocal here. But within all the other groups, the males are bigger than the females. Okay, and the sort of the direction of the effect is the same, and the size of the effect is about the same as well. So from the box plot, we see that within males, area E birds tend to be bigger on average, and within females, area E birds are also bigger on average. So we can conclude that area E birds are bigger regardless of sex. The difference in sex is not what is producing the difference in area. There are differences in both area and sex. Okay, we could try some other plots as well, so let's just quickly see if we can do some densities. Okay, so densities, I think what we can do is basically do that same setup, but instead of filling by area, we'll fill by sex. Okay, and so now we have male and female birds with each area, and so you can see here that E again is the largest within the blue and the largest within the red. It's a little bit hard to see, isn't it, because they're squished up a little bit. We can of course change the dimensions of the plot. I might as well show you that as well. So we can go fig dot height equals 10. I think these are in inches or some crazy measure. I think it's in fig dot width equals 6 maybe. Can I get it? Can I force it to be? What's happened here? Oh, I don't know. Anyway, there we go. So you can force the if you specify both the width and the height, you can force it to be a little bit different. I guess we've probably gone too far there. Not sure what that error is. Anyway, there we go. Okay, and you could do the same with the histogram. Let's do, perhaps we could grid it for a histogram. So let's jump histogram. Let's just do single one, and then we'll facet grid by sex and area. So facet grid is like facet wrap, except you use two variables, and one of the variables is used for the rows and one for the column. That's actually the wrong way round to what I want. I actually want it the other way around, because what I want to be able to do is compare within the females. I want to compare across the areas, so I want each of the areas lined up vertically. So let me swap those around. That's better. And then I also want to specify the number of bins. Yeah, so I could use something like that. This is not very good, is it? But you can get sort of the idea, right? In the males, the area E birds are shifted up a little bit. Can't really tell what's happening much in the females because there's just so few birds in some of the areas. So a histogram's just not doing well for this. But that also tells us that we should be a little bit cautious about our other ones, right? Because these don't show us sample size. So our conclusions from this need to be a little bit tempered because we don't have sample size on them. And the box plots looked quite good, right? But from our histogram, we can see that actually in area C, for example, we actually only have 2 birds. Yet on the box plot, it's enabled us to still draw a box plot. But in fact, this is all actually arbitrary. The actual location of those birds is there's one right down the bottom there and one right at the top. So the median of those 2 birds is just halfway in between them, which is an observation that does not exist. The upper quartile is the halfway between the median and the top number. So again, this is a data point that does not exist in our data. So we've got to be a little bit careful when using box plots when our sample size is small. That only applies really to C and F though. So the others aren't too bad. Okay, so I think our conclusion is probably still okay that area E birds are bigger. Right, so that's what we saw in our data, but we want to know whether that is true in our population, right? So we need to do some statistical inference. So we need to say, we need to take the information that we have in our sample and infer back to the population. So we're going to do this using confidence intervals like we discussed in the lecture on Monday. And we're going to be starting with a separate confidence interval for the males and the females so that we can infer something about the difference in the population. So this first set of code here is doing some subsetting. So we take our petrels and we subset out just the males. Notice the two equal signs here. That means is equal to. Okay, so this is saying subset the petrels such that sex is equal to male. Notice that differs from the single equal sign, which means assignment. Okay, so you do have to be extra careful when you're using equivalent to. It's two equal signs, and this really applies mostly to subsetting stuff. Okay. Okay, and so the males is just the male birds, the females is just the female birds. As you can see, 130 plus 529 is 659, so we've subset the data out perfectly. And then we've used the t-test command in order to get a confidence interval for the male right wing lengths. So you remember that we sort of read it from the bottom here. There's our sample mean, so that's the average of the males in our sample. So 388.4, and then here is our corresponding uncertainty interval for the average in the population. So you remember our confidence interval is essentially taking our best guess at what the population mean is, which will be our sample mean, the 388.4. And it's sort of adding a bit of uncertainty, the uncertainty coming from the uncertainty in the sample mean. So it's sort of adding on plus or minus twice the standard deviation of the sample mean to get these numbers here. So our conclusion from this is we're 95% confident that the male birds are between 387.6 and 389.2 on average. Right? So we're 95% confident that the mean right wing length of male birds in the population is captured by the interval 387.6 to 389.2. So we could just say somewhere between. Okay, so this in the population is important, right? Let's put some asterisks around that to bold it up. That's the difference. So that's what the confidence interval is essentially giving us, right? That's what our inference process is giving us. It's giving us, instead of in the sample, it's giving us in the population, right? Which is a much more powerful thing. Now we want to do the same thing for females, so let's just copy and paste that line and do the same thing. And we'll run them both. So there's the female one there. Okay, so we could do the same thing. So we're 95% confident that the mean right wing length for female birds in the population is somewhere between 383.5 millimeters and 387.0. And what we notice that these two uncertainty intervals do not overlap. So we're at least 95% confident that males are bigger than females in the population. Right, because the highest the females are is 387 on average, and the lowest the males are is 387.6. So males on average are higher than females. Now Let's do the same thing for the different areas. So we can run this code block here. So this is exactly the same thing, isn't it? We're just subsetting out area A birds and then doing the confidence interval. Not sure why that didn't run. I think I just selected some of it instead of running the whole lot. Okay, so area A birds, we're 95% are between this interval here. And we could copy and paste this for all of the other areas, couldn't we? Right, so we could make a bunch of data sets. So we've got area B, area C, area D, area E, area F. Right, change the subset conditions to B, C, D, E, and F, and then change the use of those subsets in t.test. Right, and when we run all that, we'll get a bunch of different t-tests. Okay, and we could then compare them, right? So if you look through and you look at area E, remember that one was the big one, wasn't it, in our sample? We see that we're 95% confident that area E birds on average are have a mean of between 392.2 and 395. And if you look at all of the other ones, if you look at the upper interval, they're all lower than 392. Right, so all these intervals is that area E birds are larger on average. Area E birds in the population have a larger mean right wing length. Now remember, so we're not talking about the right wing length of all area E birds, rather we're talking about the average of them, right? So individuals are going to be spread a lot further than the range that we're giving here, right? So this is the uncertainty for the mean. Obviously the individuals will be even further away from the mean than this uncertainty interval, right? The mean, of course, would have a much smaller uncertainty than individuals would have. We'll look a little bit about how we can get uncertainty for individuals in semester 2 when we look at modelling. Now this is a little bit cumbersome because we're copying and pasting code a whole bunch 6 times over. And whenever we do that, there was a number of places that we could have made an error, right? We could have made a typo here, we could have made a typo here, we could have made a typo here. There's lots of ways that could go wrong, and it's a little bit cumbersome to compare everything. So this next set of code is some fancy schmancy code in order to do all of the above in one step. Okay, so if we run that, then we get a nice concise, I'll make it a bit wider so you can see that. You get a nice concise summary of the above. It's the exact same information, it's just been tidied up a bit. So you can see that for each area we have our estimate. So that's our estimate for the right wing length, for the mean right wing length. We've got a bunch of other information that we will discuss later on. And then we have our confidence low and our confidence high. So there's our confidence interval there. So you can, again, you can easily see the area E here, the lowest it can be is 392.2, but the highest all the other areas can be is 391. So area E again is higher than the others. Just a sort of a note about how this code works, you're not expected to be able to obviously write this yourself. Feel free to copy and paste it if you want to reuse it. But just to sort of quickly go through what's happening, the tapply function, what that does is it takes a variable here, the right wing length, and it breaks it up into the different areas. So essentially it does the subsetting for us automatically, and on each of those subsets it's running t-test. Okay, so essentially that's doing the code that we just did there 6 times in that one line. Then we save the output and then we do some tidying, right? So that we take our t-tests, which is going to be a list of 6 different tests, right, which the tapply function will give us, and we're going to run broom tidy on it, and that essentially produces this little data frame here, right? So it produces a single row for each of the things and then returns a list, and then dplyr bind rows binds them up so that they're in a single data frame. So essentially puts all the rows, combines all the rows together into a single data frame. So we've got our combined data here, is that data frame. And so we could use that to do some plotting, right? So we could potentially plot all of this. So we're going to go ggplot. We're going to use our combined data, and then we're going to use put some points on where our x is our area and our y is our estimate. Right, so there's our mean right wing length. Let's perhaps add that in. So we can see that area E is bigger, but we've got no uncertainty on there. We've got no confidence bars on there, and we could use G on bar for that. So we're just going to take our G on point and replicate it. G on error bar. And if we have a look at the help for G on error bar, you can see that there's a bunch of them. There's crossbar, error bar, that's the one we'll use. Line range, we might try these ones out as well. Point range. And if we go all the way down, you can see the aesthetics that they take in. So that's the things that are inside our AES bit down here. Take in X, Y min and Y max. So instead of a Y, it takes in Y min and Y max. And that's of course because we need our confidence low and confidence high. So we want to take confidence low, that'll be Y min, confidence high will be Y max. So Y min, conf low, and Y max, conf high. There we go. So there's our confidence intervals, and again, you can see here that area E is larger than all of the other areas. You can see also that that we're less confident about areas C and F, which of course is because we've just got less data there. We're more confident about the other groups because we've got more data there. Okay. There's other ones as well, so I think point range does it all at once. Let's have a look at point range. So I think we can just change this to point range and put all this into there instead. So I think that does it all in one, so it puts the point and the lines. Yeah, so that's another one. In fact, I like that better, I think. You know, the width of these lines is meaningless, isn't it? So I think this is actually a little bit nicer. Okay, so that's point range, where you give the X and the Y for the point, and then the Y min and Y max for the range. And you can do it horizontally as well, just switch the roles of X and Y. Okay, so perhaps I'll show you that as well. Y, X, and these will be X min and X max. And then we'll change our Y axis label. So that's the other way to do it. So again, area E is the highest mean right wing length. Okay, so this is telling us that, so our one way up here is telling us that, we saw a difference between male and female birds in our graph, in our sample, and that we can infer from our sample, essentially due to the size of the sample and how much sample to sample variation we would expect given that sample size, we can infer that in the population there's a difference as well. And we can also infer the same thing about the areas. So in the population we can infer that area E birds are bigger. Now the other way to do the right wing length in terms of sex, so differences between sex that we did up here, and this one here, the other way to do this is to do a single confidence interval. Okay, and we can do this because we've just got two groups. And when we have two groups, then we could look at the average difference between the groups. So instead of looking at the average for one group and the average for the second group separately, computing a confidence interval for each one, and then comparing the confidence intervals, we could instead look at the difference between the average right wing length of males and females, and then produce a confidence interval for that difference. So this is what this syntax here does, right? So we're t-dot testing right wing length in terms of sex, and it only works for two groups. Okay, and so this is the output you get. You get the mean in group 1 and the mean in group 2. So group 1 here is the females and group 2 is the males. So these numbers are exactly the same as what we had before. And so you could see from this that the mean difference between the two would be 385.23 minus 388.4, which is going to be about 3.1. So the mean difference in right wing length between male and female birds in our sample is 385.26 minus 388.44, which is about 3.1 millimeters. Minus 3.1, isn't it? Right, females minus males. So females are about 3.1 millimeters smaller on average than males in our sample. Right, so that's just in our sample, but of course we've got we know something about how the mean difference is going to vary from sample to sample, right? So it's going to follow a normal distribution as well, just like the means themselves follow a normal distribution. The difference between two normal distributions is also a normal distribution, right? So that mean difference is also going to follow a normal distribution, and we can again add our confidence interval around that once we know what the standard deviation of the mean difference will be. That formula was actually given to you on the slides, but of course the computer knows it as well, and so the computer has worked out that standard deviation and has computed a confidence interval for us. So we're 95% confident that the mean right wing length, I should actually put between female and male, right? It's ordered, isn't it? Between female and male birds in the population is between minus 5.1 and minus 1.2 millimeters. So females are about between 1.2 and 5.1 millimeters smaller than males on average in the population. Okay, so they're both negative here just because we started with minus 3.1 and added and subtracted the standard, twice the standard deviation. So if you subtract something from minus 3.1, you get something a little bit less than minus 3.1, so that's why these are both negative. Nonetheless, our conclusion are that they're both the same sign, right? So in either case, females are smaller, which is our conclusion. Okay. Now we're not going to be able to conclude that they're smaller if 0 was a possibility within this interval. Okay. So let's try this out below. Let's try and be more confident. So we're only 95% confident that there's a difference here. Maybe we can be more confident. So what do you think will happen when we increase our confidence level? So what I would expect is, because we want to be more confident with our answer, we're going to give a less precise one. So we're going to give a broader interval, because that will capture the truth more of the time, a higher proportion of the time, right? So sure enough, we get the exact same numbers from our sample, because our computer from our sample hasn't changed, but we get a wider confidence interval. So our conclusion here would be we're 99% confident that the mean right wing length between male and female birds in the population is between minus 5.75 and minus 0.62. So females are between 0.62 and 5.8 millimeters. 0.6 and 5.8 millimeters smaller than male on average in the population. Okay, and you can expect that if we increase the size again at some point, so say we could be 99.8% confident, then again we're still confident of the difference because these are both negative numbers, right? But we're getting, the magnitude of the difference is getting quite small at the high end. So at some point, say when we go to 99.9, okay, so now the difference is somewhere between minus 6.5, so females are smaller by 6.5 units, or females are bigger by 0.1. So at some point, if we want to be super confident about what the difference is, 99.9% confident, then we've got to admit that the difference could in fact be 0. Okay. Okay, so as we increase, so if we want to be 99.9% confident, then females are on average 6.5 millimeters smaller to somewhere between 6.5 millimeters smaller to 0.11 millimeters larger than males. Be the same in the population. Right, so as we increase our level of confidence, the length of the confidence interval gets larger, so our decision making ability gets poorer. Right? We essentially are giving a vaguer answer. Right? We're giving a broader answer. Nonetheless, we're more likely to be correct. It's just a less useful answer, perhaps. So there's a trade-off between being confident about something and being able to give a useful answer. Increasing the sample size, of course, will decrease the length of the confidence interval for the same level of confidence. Right, this makes sense, right? Because as our sample size increases, our sample mean is going to vary less from sample to sample. So there's going to be less uncertainty associated with the sample because essentially we're covering more of the population. Right, so if we want to be more confident while not increasing the length of the confidence interval, what you've got to do is increase your sample size. Then for the same confidence interval length, you'd be able to have more confidence. Because the increase in your confidence interval from being more confident would be traded off by the increase in your sample size, which makes the confidence interval, which makes the uncertainty in the sample mean lower. Right, let's just knit that up, make sure it all works. Make sure we get our document done. It looks okay. We're done.